Hello everyone, welcome back to the series where I attempt to write the world's smallest Blink program for atmega328p microcontroller from Atmel. Um, so from the last video, we have the following observations. We tried to generate the program for the normal Blink program. We got 924 bytes from the Arduino software, and then we used AVR GCC, the cross compiler for AVR microcontrollers. We got 1204 bytes with no optimization, and then we used the optimization OS, which means optimize for size, to reduce the binary size to 178 bytes. In this video, we will try to further reduce the program by removing some of the assembly sections that we don't need. But before we remove it, let's first see the assembly that make up the program. The program for Blink 1 is this blink.elf. That is the compiled file. To see the disassembly, we write avr dash uppercase s and then the name of the executable. So here we have the code that is generated by the compiler. What we are interested in is this main. That is what's happening over here. This is the code that we wrote, and this is the translation to the machine instruction, which the microprocessor of the controller understands. What we need to do in this video is I'm trying to get rid of all the other codes if they are not important. So let's see what it is doing, and then we will see if we can remove it or not, depending on the functionality. If it is useless, we'll remove it. If it is not, if it is useful, then we'll try to keep it. So what happens here? What happens when we just turn on the microcontroller, when we give it a power? What happens is the program counter is going to be set to a particular value. Let me just open the datasheet and see the AVR memories. This is the program memory. When we turn on the microcontroller, or when we give it power supply, power on reset is going to occur, and the program is going to jump. The program counter is going to be set to this location, somewhere on the boot flash. It doesn't always have to start from here. You can actually modify the fuse bits to make the program start from here, from the top of the program memory. But as it stands in the Arduino Uno board, the program counter is configured to start from the bootloader, which is why you see the 3 blinks when we just plug in power. But anyway, the code that's here is then going to set the program counter to the top of the flash, and which is where our code lives. So let's assume the microcontroller starts executing from here, from the first line. The instructions that we have here is called the interrupt table. They are essentially just jumps when a certain hardware conditions are met. For now, we don't need any of those things, so we can get rid of the interrupt vectors. So what's happening here is the first instruction is to jump to this label, setor's end, and the rest is to jump to bad interrupt. So whenever a bad interrupt is happening, the program counter is going to set here. Whenever there is an interrupt happening, the program counter is going to be set to whatever the interrupt that caused it, for example here, and then since we are not handling it, it will jump to the bad interrupt handler, which is here, and the bad interrupt handler is going to jump to the address 0, which is basically to the reset vector. And from the reset vector, it will jump to this setor's end label. And what it is doing here is it is doing something useful. So let's see what it's actually doing. The first instruction that it is executing is XOR operator to R1 with itself. So when we XOR any register with itself, it will become 0. And by the way, this R1 register is called the 0 register because it is always supposed to its value is always supposed to be 0. That's what AVR thinks. The AVR compiler is always going to assume that the value of R1 is 0 from now onwards. Okay, the next one is outputting R1 to this memory location on the RAM, and whatever this register is, it is setting the value to 0. So let's go and see in the register description what that register is. So the value was 0x3f. So it is sreg. It's called the states register. This is not important for our program, so we don't really need that instruction. Okay. And then what it is doing is it is moving the value 0xff, which is 255, to R28. Okay. And then it is moving 08, FF. It is moving FF to 28 and 08 in hex to R29. And then it is writing the value of R29 to the address of this location. And which register is that? Well, let's go and have a look at what that register is. Um, 3E is apparently stack pointer high, and 3D is stack pointer low. So what's happening right now is the stack pointer is being set to some values, and the values are 08FF. And what that value is I think it is the highest value in the memory in the RAM, 08FF. Normally the stack is supposed to be the highest, the farthest value from the data region. So normally our variables, global variables, are going to be stored in the RAM. In order to avoid any kind of stack overflow, the stack is set to the highest value. So this is essentially what's happening is it is just setting the stack pointer, these four instructions, and then it's calling to main. The program is not supposed to return from main, but if it does return from main, it is jumping to this exit level. We have it here. The exit level is going to clear interrupts, so no further interrupt is going to occur, and then it will come here and do an infinite jump. It will just stuck here, but normally the programmer should not allow to return from main. That's why you see while one, something like this, excuse me, something like this while one. We don't want to return from main, but if we do allow to return, the compiler adds this infinite loop in case. So we don't need these two things as well. Clear and do it again. It's very weird because whenever I resize, I lose some of the data. I don't know why. So it turns out we don't need anything of those things. They are not useful. We don't have to initialize the stack as we are not using it in the main. Let me also explain what's happening in the main so that we make sure that none of these things is required before we get rid of it. In the main, what's happening here is clear. FF is being loaded to R24, and then R24 is stored in the location 0x04. And what that register is from the datasheet, register number 4. Here it is. It's DDRB. So what it is doing is saying DDRB is equal to R24, which is FF. So essentially, this C instruction is converted into assembly in those two lines. Next, output R24 to location number 5, and location number 5 is port B, and now it will make sense that port B is FF. So it's actually very interesting to see how the C statements are translated to assembly. And then the next few instructions, they are responsible to cause this delay of 1 second. It's making some useless loops to make the CPU busy until it wastes 1 second. Next thing is nothing spectacular. It's moving R1 to number 5, to the location number 5, which is port B. So it's actually doing this thing. And R1, it was 0, if you guys remember earlier. Yeah, this instruction. And then the delay of another 1 second is basically caused by the rest of the loop, and then finally jump to the top of the while loop. So this instruction is basically is causing the program to come and execute these things again. So that's very interesting to see the actual assembly instruction for the main method, or yeah, the main function, you could say that. So it turns out we don't actually need anything except maybe this exclusive OR that sets are 1 to 0. But anyway, let's get rid of everything else except the main, because nothing is useful. We are not using the interrupters. We don't need to set the stack because we are not using it at all here. We just saw that none of this has anything to do with the stack. In order to remove everything except our main function, we can pass some parameters to AVR-GCC, which is, if I am right, no start files. Let's save that. Clear, remove the elf file, and make blink1.elf. We have the elf file, and let's see the size now. Make blink1.bin first, and then ls. Yeah, it's actually 46 bytes. Wow, that's a very good improvement. By the way, you can also know the size using the AVR size, and then we pass the executable, not the binary, but the executable. Yeah, 46 bytes. So let's keep track of the size. We are certainly making some improvements. Now it is 46 bytes without startup code. By the way, the startup code is really important. We don't see all the importance in this case, but normally it is used to relocate the data section from the flash to the RAM. If we see on the AVR memories, there are actually two types of memories: the region where the program is stored, and the region where the peripherals and the global variables are stored in the RAM. So normally it is the startup code that take care of moving or relocating the global variables into the RAM. But in this case, we don't have any global variable. That's why we did not see the code that relocates it. Also, the startup code is responsible for clearing the BSS section. Maybe one day we will see that. But for now, let's disassemble the new program and see what is inside it. AVR dump. And yeah, nothing is there except the main program. So that's it. That's it for the video. We have successfully reduced the program file from 178 to 46. How many minutes is it? So in the next video, I am going to try to modify this code to make things better and hopefully get even smaller program. Thank you for watching, and I will see you in that video.